Hello and welcome to this video on all-day efficiency of a transformer. By the end of this video, you will be able to define a transformer and say what are the losses present in a transformer, able to give an expression for the efficiency of a transformer. We have to able to answer what is meant by all-day efficiency of a transformer, what is meant by energy efficiency of a transformer, and how to express the efficiency of a distribution transformer, and also to give an expression for the all day efficiency of a transformer. Okay, so basically a transformer is a device. It is a static piece of device which is used to transfer electrical energy from one circuit to another circuit through electromagnetic induction, and this is done by maintaining the frequency the same, that is the frequency at the receiving end, or the secondary side of the circuit will be the same as that at the supply side of the transformer. Basically a transformer has two sides, a primary and secondary. So primary side is connected to a supply, an alternating supply, and at the secondary side you will get the induced voltage or current, which is by induction, mutual induction. Okay, and that voltage will be of the same frequency as that of the supply voltage. And a transformer is not a device, not an ideal device, and there will be some losses. And in a transformer, the losses that occur in a transformer are the copper loss and the core loss. The core loss is because the transformer has mainly two parts, a core, a magnetic core, and two sets of winding. One is called the primary winding and the other one is called the secondary winding, and the one to which the supply is connected is called the primary, and the one to which the load is connected is called the secondary. And this magnetic core is to make the flux from the primary to link with the secondary. And you know the basic principle of electromagnetic induction, and I am not going in deep to that. Okay, so the losses occurring in a transformer are basically copper loss and core loss. Core loss is the loss occurring in the core of the machine, and copper loss is occurring in the windings or the coils when current flows through it. So the efficiency of a transformer is given by efficiency eta equal to output in watts divided by input in watts. That is the case of a normal transformer or normal efficiency expression, and it will always be less than 100 and somewhat nearer to 100. But in the case of a distribution transformer, we will not be able to describe its efficiency by the expression given in the previous slide, which is output in watts by input in watts. And the transformer used for supplying lighting and general network, that is the distribution transformers, have their primaries energized all the 24 hours of the day, although their secondary supply little or not load much of the time during the day, except during the house lighting periods. So it is not always connected to the load, but the supply is always energized. It means that whereas the core loss occurs throughout the day, the copper loss occurs only when the transformers are loaded, because we know that copper loss occurs when current is flowing in the circuit. Hence it is considered a good practice to design such transformers so that the core losses are very low and the copper losses are relatively less important because they depend on the load or the load current. The performance of such transformers are compared on the basis of energy consumed rather than the power energy consumed during a certain period. Usually it is done during 24 hours. So for a distribution transformer, the losses that occur are the copper loss and core loss, but only the core loss is of most importance. The copper loss occurs only when it is loaded, and for such transformers the efficiency is defined as an all day efficiency, that is the efficiency over a day. And the equation is like this: efficiency all day equal to output in kilowatt hour, not in watts, in kilowatt hour, divided by input in kilowatt hour for a duration of 24 hours. So it is the ratio of output in kilowatt hour, that is energy in kilowatt hour by energy in kilowatt, input energy output in kilowatt hour by energy input in kilowatt hour.